Hey guys, how's it going? Mr. Mitchell here. In this video we're going to go over question 2 from the 2021 SQA Advanced Higher Physics exam paper. So let's get started. Question 2 says a cyclist is using an exercise bicycle. A large flywheel forms part of the exercise bicycle as shown in figure 2a. So there's the cyclist in the exercise bicycle and it shows the flywheel and the screen labelled. It then says the rotational motion of the flywheel is monitored by sensors at its outer edge. Data from the sensors is used to calculate equivalent linear speeds which are displayed on the screen. Part A says the cyclist is pedalling steadily. A constant linear speed of 6.7 meters per second is displayed on the screen. Part 1 says the flywheel has a radius of 0.35 meters. Calculate the angular velocity of the flywheel, and you'll see there's 3 marks available for this. Well, writing down what we know from the question, we're trying to find the angular velocity omega. We know that the linear speed v is 6.7 meters per second as mentioned up here, and the radius r of the flywheel is mentioned here, 0.35 meters. So writing down our equation relating angular velocity, linear velocity and radius, we have v equals r omega. Rearranging for omega, we can divide both sides by r to get omega equals v over r. Substituting in the numbers gives 6.7 divided by 0.35, and putting that into your calculator should give you an answer of 19 radians per second. A part 2 says the cyclist now stops pedalling for 5.5 seconds and the flywheel slows down due to a constant frictional torque. The flywheel has a constant angular acceleration of minus 2.4 radians per second squared. Determine the number of revolutions made by the flywheel in this time, and you'll see there's 4 marks available for this. Well, what we want to do is first find the angular displacement theta and then divide this by 2 pi to find the number of revolutions. So we're trying to find theta. We know that initial angular velocity omega naught is 19 radians per second, and remember that's the answer to part 1, but we're using it as initial angular velocity here, not final angular velocity, because the flywheel is slowing down and this was the angular velocity that it's doing to begin with. We don't know what final angular velocity omega is because we're not told that it comes to rest. Angular acceleration alpha is negative 2.4 radians per second squared, where the negative shows that it's slowing down, and time t is 5.5 seconds. And I'll put a star next to theta because that's the one we're trying to find. So we want to use an equation of angular motion that doesn't have omega in it. So we're going to use the second one, which is theta equals omega naught t plus a half alpha t squared. Substituting in the numbers gives 19 times 5.5 plus a half times minus 2.4 times 5.5 squared, and put that into your calculator should give you an answer of 68.2 radians. Now remember we're not finished because in order to find the number of revolutions made by the flywheel, we need to divide our angular displacement by 2 pi, because remember 2 pi radians is the angular displacement for one full revolution. So we can do 68.2 divided by 2 pi is equal to 11 revolutions, where we've written the final answer as 2 significant figures because you'll see in the question here we have 2 significant figures there, we've got 2 there, and so on. A part 3 says the cyclist reduces the frictional torque acting on the flywheel. The cyclist resumes pedalling until the screen again displays a linear speed of 6.7 meters per second. The cyclist then stops pedalling for another 5.5 seconds. State how the number of revolutions made by the flywheel in this 5.5 seconds compares with your answer to A part 2. Justify your answer, and you'll see there's 2 marks available for this. Well, we can say that the number of revolutions will be greater, i.e. greater than the number in A part 2. And we can justify this by looking at this equation, tau equals I alpha. So this says that torque tau equals the moment of inertia I times the angular acceleration alpha. And from this equation we can see that a reduced frictional torque, which we're told about in the question, will produce a smaller angular acceleration. And that's because if we rearrange this for alpha we get tau over I, and if moment of inertia doesn't change, it stays the same, then a smaller tau will give us a smaller alpha because they're directly proportional. So we'll have a smaller angular acceleration during the 5.5 seconds, meaning the wheel will have a greater angular displacement. And you might be thinking, well, how does a smaller angular acceleration lead to a greater angular displacement? Well, we can look at our working to part 2 to see this. So we're saying that with a reduced frictional torque, this angular acceleration alpha here will be smaller. So because of this negative, you end up taking away this whole expression from this number on the left. So if this angular acceleration is a smaller value, then you're taking away a smaller number from your number on the left. So that means your angular displacement theta will be greater. Lastly, part B says the frictional torque is produced by a brake pad in contact with the flywheel. Figure 2b shows 4 possible positions A, B, C and D at which the brake pad could come into contact with the flywheel. So you've got your flywheel there, you've then got your points A, B, C and D, and it shows us the axis of rotation directly in the middle of the flywheel. It then says the brake pad would apply the same force in each of these positions. State which of these positions would allow the brake pad to produce the greatest frictional torque in the flywheel. Justify your answer, and notice how this is worth 2 marks. Well, if we think about our equation for torque in terms of force and distance from the axis of rotation, we have tau equals Fr, and if we're told the brake pad would apply the same force in each of these positions, then force stays the same. So we only really need to look at how the distance from the axis of rotation will affect the torque. So because tau and r are directly proportional, you can see that point B will have the smallest distance from the axis of rotation and therefore the smallest frictional torque, whereas the point that is furthest away from the axis of rotation, this point D, will produce the greatest torque. So we were asked for which one is going to produce the greatest frictional torque, so we could say position D, and that's because a greater torque will be generated on the flywheel by applying a force at a greater distance from the axis of rotation. And we've already said that torque tau equals Fr, where tau and r are directly proportional and F stays the same. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video one of these, subscribe to the channel, and I'll see you in the next one. Take care.